Alright, so we're going to start this insurance assignment video. We start with the first question from 3.2 and 3.5, translations and scale changes. So essentially we have t mapping xy to x plus h y plus k is applied to any function y equals f of x. What is the resulting equation? So one of the things that's really important for this chapter test is that you recognize that whatever the operation is in the rule, you're going to substitute into the equation with the opposite operation as the rule. So here we have x plus h in the rule. In the equation, we're going to substitute that x with the opposite operation, x minus h. The same with the y. We've got y plus k, so we would substitute into the equation with y minus k. Here's a quick example. So if we let t mapping xy to x minus 4, y plus 5, we'd be moving to the left 4 and up 5. It's being applied to this function, y is equal to 1 over x plus 3 minus 4. Then what happens is our y is going to be replaced with the opposite of y plus 5, which is y minus 5. The x is going to be replaced with the opposite of x minus 4, which is x plus 4. And then we just have to go about simplifying this. We would want to add 5 to both sides to simplify, and then just simplify whatever the denominator is, and this is what you're left with. So, the asymptotes of the original function would have been x equals negative 3 and y is equal to negative 4. The way I can tell that is if I put negative 3 in for x, I get a 0 in the denominator of the fraction, and we know that we can't divide by 0. The other thing that I know is that this right here, that part of the original equation, is never going to be 0. You can't take 1 of something and divide it by something else and end up with 0 here. So since this part can never be 0, y can never be negative 4. That's why we have an asymptote at y equals negative 4. Now that I know what the asymptotes are, this is a vertical line at x equals negative 3. This is a horizontal line going through negative 4 on the y-axis, but it's still a horizontal line. What happens to these under this transformation? Well, everything's going to get moved to the left 4 and up 5. So this asymptote is getting moved to the left 4. Where is it going to end up? It's going to end up at x equals negative 7. This asymptote is getting moved up 5. Where is it going to end up? It's going to end up at y equals 1. So there's a quick example of what of how you can use this this rule in these kinds of problems. Okay, the second thing we're going to talk about is size changes. So here's our size change. It's being applied to the function y is equal to f of x. What's going to be the resulting equation, and what's the description of how the function has been transformed. So here is the resulting equation. So we have, again, replacing in the rule with the opposite. So we have b times y in the rule. So this would be y divided by b, or y times the reciprocal of b, which would be 1 over b. And that's probably the best way to think of it, is multiplying by the reciprocal instead of dividing. That way you don't do this as b divided by y, which some people tend to do. So think about how I would undo this. I would multiply by 1 over b. So I'm going to replace in the equation with 1 over b, y with 1 over b. So the same thing with this a times x, that's going to be x divided by a, or 1 over a times x. If your a value, or the number you're multiplying by, is greater than 1, that means that the function is going to be stretched out. If it's between 0 and 1, so for example 1/2, we're going to use the term shrink. So here's our example. We have this size change happening to the parent cubic function. This would mean that we're stretching by a factor of 3 horizontally. This would mean that we're shrinking by a factor of 1/4 vertically. So if you imagine that, the graph is really going to get dramatically fatter than the original cubic function. But I know that's not necessarily a technical term, but maybe the easiest way to visualize it. So in the rule, we have 1/4 times y. We're going to replace in the equation with 4 times y. In the rule, we have 3 times x. We're going to replace in the equation with 1/3 x, or you could use x divided by 3. Remember that anytime you replace, see x is being cubed, whatever I replace x with, that also must be cubed. So this 1/3 x is getting cubed. So to solve for y, we're going to divide both sides by 1/4, or divide by 4 or multiply by 1/4. Now we have to cube the 1/3 x. So 1/3 cubed is 1/27th, x cubed is x cubed, and then we just have to multiply those two fractions together to get 1/108 x cubed. Remember that the rule is a description of how points on the graph are transformed. So let's say you have x-intercepts at +2 and 3, and you have this size change. What's going to happen to those x-intercepts? Remember that the x-intercept is a point. It's the point 2, 0. The rule is a description of how points on the graph are moving or are being changed. So this point 2, 0 is going to turn into the point 6, 0. This point 3, 0 is going to turn into the point 9, 0. So you can see that the x-intercepts will still stay the same. Okay, so the next one is how can you identify asymptotes of functions such as y equals 4 divided by 2x minus 5 plus 3 without graphing? Well, the first thing is we should know, I spoke about this earlier, you have a 0, this right here, this 2x minus 5 can never be 0. So you take that 2x minus 5, you say, well, what if it was 0? If it was 0, that's where my asymptote's going to be. It's going to be this line that I approach, but I'm never going to be able to touch. So I set that equal to 0, I solve for x, and there's the equation of an asymptote. X equals 5 halves, or 2.5. So on my function, I would have a vertical line going through 2.5. For the horizontal asymptote, this piece right here cannot ever be 0. I'm taking 4 of something and I'm dividing it into 2x minus 5 pieces. That will never end up being 0. So since that can never ever be 0, y will never ever be 3, which means you will have an asymptote at y equals 3. So that's just a way of, without graphing, looking at an equation and trying to determine what the asymptotes of what you should consider to be a hyperbola would be. Okay, finding the equations of a transformed graph. So the first thing we would have to do, let's say this is the graph that we're given, we have to figure out how, what is the parent function and how has it been moved. So I can look at this, I can see it's the parent, or it's the cubic function, and I can see that the point 0, 0, that point right there, has been moved 3 units to the right and 2 units up. So that point 0, 0, where the cubic function used to be, is now at 3, 2. So I can use that to write a rule, x plus 3, y plus 2. Now that I have the rule, I can now take that rule and I can apply it to the parent function. So I had a parent function of y equals x cubed. I'm going to substitute in with not y plus 2, but y minus 2. I'm going to substitute in with x minus 3. And remember, keep it inside of parentheses and cube it. Solve it for y and we get this, x minus 3, the quantity cubed, plus 2. Another thing that you want to do, because it doesn't take long to do, is just check an answer by using another point that is on the graph. So I chose to use this point, 4, 3. If I put 4 into the function, the x coordinate in, I should get 3 out. So let's try it. I'm going to put 4 in for x. 4 minus 3 is 1. 1 cubed is 1. 1 plus 2 is 3. So when I put 4 in, I got 3 out. That tells me that, yeah, the equation that I came up with up here looks like it's going to work. You could also use the point 2, positive 1 and see what happened. If I put 2 in for x, I'd have 2 minus 3 is negative 1. Negative 1 cubed is negative 1. Negative 1 plus 2 is positive 1. So the point 2, 1 is on the graph. So you can just quickly use other, other points that are on the graph to check your answer. Okay, how can you determine an equation for a graph of a composite function? Okay, so determine an equation for and graph a composite function. I didn't really do much with the graphing. I probably shouldn't have put that on there. But to determine an equation, so for example, f of g of x, you're essentially putting the entire equation of g of x into f. So the domain of the composite function, this is where things tend to get a little tricky. How do we determine domains of composite functions? So over here I've got an example of, let's say we're doing t after we do s. So that means we have to find the domain of s first and see if there are any restrictions on it. If there are any restrictions on the domain of s, that means that there are x's that won't work first. So those x's won't work at all. Even if I do t after s, that all of s happened first, so since s happened first, any restrictions on that domain hold true for t after s. So let's do an example over here. We have these two functions. Let me go back to this. So you have to find two domains. So you find the domain of s, and then you find the domain of t after s. If there are any restrictions on either of these functions, then you include those restrictions in the domain. So here's an example. We have g of x is equal to the square root of x plus 5. F of x is equal to x squared plus 7. The domain of f after g. We're doing g first, so I look at the domain of g. We have a square root function, so that means that what's underneath of the square root must be greater than or equal to 0. So I set that x plus 5 greater than or equal to 0, and I solve for x. So the domain of g is x is greater than or equal to negative 5. Now I do f after g. So when I do f after g, I'm taking all of g, I'm putting it into f, so I'd have the square root of x plus 5 squared plus 7. That's going to become y is equal to x plus 12. Its domain is all real numbers. Well, the domain of the composite function, even though I just found the domain of f after g as all real numbers, the domain of that composite function is all real numbers, the problem is that g had a restriction on it before I found the equation, so therefore this right here is the domain of f after g, because g happens first. So that restriction holds true for the rest of the composite function. If I were to graph this right here, just that, if I were to substitute that into my graphing calculator, what I would look like, it would look like a line that starts at negative 5 and then continues on forever, but the nothing to the left of negative 5 would be represented. Even though algebraically that square root is undone by that square, when you substitute it into the graphing calculator like this, the line would start at negative 5 and continue on forever. Okay, so how do we determine the inverse of a function? To find the inverse of a function, you're essentially switching x and y and solving for y. So I have a nice easy one here. To find the inverse of y equals x cubed, we switch the x and the y, and we solve for y. So we have y is equal to the cubed root of x is the inverse of y equals x cubed. how do you find, or how can you graph the inverse of a function using points on the original function? Well, there is a transformation that's going on here. We're taking all the points x, y, and we're making them y, x. So if you have a, b on the graph of y is equal to f of x, then BA is going to be on the inverse. So if I wanted to graph an inverse of a function, all I would have to do is switch the x and the y coordinates and then graph those points. The relationship between a function and its inverse, the graphic relationship, is that they are reflections over the line y equals x. Here's a representation of that. We have y equals x cubed. We have y equals the cube root of x. Here's the line y equals x, and you can see the relationship, that they are reflections of each other over that line. This is one thing that should have been in the notes. Verifying that a function is an inverse. You need to show that f inverse of f of x equals x and that f of f inverse of x is equal to x. You have to show both, because we know that the composite of functions is not commutative, so that we have to show that f inverse of f of x equals x. Yes, that might be true, but we also must show that f of f inverse of x equals x. Okay. Alright, how can the domain and the range of the inverse of a function be determined? So one thing that you can do is just switch the domain and the range of the original function. And I can see that I didn't fix this. So if I looked at this, the domain of this function would be x cannot equal 2. Okay, so the domain of this function would be all reals except 2. The range would be all reals except 1. The inverse of this function, and I'll let you come up with that algebraically, the inverse of this function would be 1 over x minus 1 plus 2. So that would be the inverse of that. You probably want to double check that, make sure you know how to actually come up with the inverse of this function. But one nice easy thing to recognize is that the inverse, the domains and ranges actually just switch. So what used to be the domain, all reals except 2, is now the range of the inverse. The same thing with the range. The range is all reals except 1, so that would be the domain of the inverse. And if you think about it, it makes sense. We're essentially switching the x's and the y's, so if that's what's going on, then the domain and the range should be switching as well. So here we have the last one. Given a point AB on a function, what's one point that you know will be on the inverse? Again, we're switching the A and the B to BA. Alright, last thing is even and odd. The algebraic definitions for even and odd. The algebraic definition for even is f of negative x is equal to f of x. For odd, it's negative f of x equals f of negative x. You will be asked to prove. I didn't include this in the notes, but you will be asked to do a proof on your test, similar to the one that you did on your quiz. So you'll need those definitions to do the proof. Remember that really it just comes down to substituting in negative x and turning that into negative 1x and algebraically simplifying. For the odd one, you want to multiply f of x by negative 1 and then do the same thing with the f of negative x, put negative x into the function and try to algebraically manipulate it down to where the left hand side and the right hand side look the same. Given a point AB on an even function, what's one point you know is also going to be on the function? Here's AB. I have the absolute value function here. Let's say it's in quadrant 1. AB is in quadrant 1. If I reflect it over the the y-axis, it becomes the point negative AB. So what's that mean? Well, essentially what's happening is we're negating the x coordinate for an even function. So If it's on an odd function, I've got the cubic function down here. Let's say I've got the point A, B. Remember that the odd function is 180-degree rotation symmetric with respect to the origin. I rotated 180 degrees around the origin. It lands on top of itself. So what's happening? Not only is A becoming negative, but B is becoming its opposite as well. So if I have the point, for example, well, 2, 8 is on y equals x cubed. So another point that I know is on the function without even looking at it would be negative 2, negative 8. So hopefully this helps. Just make sure you leave a comment in the YouTube thing. That way I know that you watched the video, and that is it.